Hello, this is presentation 5 for Engineering 305, Design of Experiments. This is the outline of what we're going to discuss today. And so the main elements of a design of experiment is first there's the goal. In reference to the response variable, the goal is to maximize, minimize, or match the target value of a certain response variable according to certain factors used to predict the response. The second element is factors, which are the elements that go into the formulations for predicting the response. And the third are levels of the factors. These are different settings of a particular factor, often set in either 2 level, being low or high, or a 3 level, which is high, medium, or low. So to create the design and perform experience, to create the design means to configure the factors and levels that will be used to achieve the goal. This means creating different combinations of levels of each factor. Each combination will correspond to a particular pattern. This pattern is displayed in the form of plus and minuses, indicating a high or low setting, respectively. Sometimes there's a middle 0 symbol if there's a third setting, in addition to high or low. In a full factorial design, we would come up with all possible patterns given our factors, but it is preferable to gain the most statistical information from the fewest trials possible because it is less expensive to do fewer trials generally. Once the patterns are determined, to perform the experiments means to collect response data for those patterns that were generated in the design. The results, consisting of the response variables, are recorded. Then, analysis is done on the results by fitting the model in SAS-jump. 2 possible models is a screening model, which is linear, and a response surface method, which is quadratic. In a regular screening design, the model is generally linear. It could use multiple regressive model if you have more than one predictive factor, or generally the underlying model used in a response surface method is quadratic or second order model. There are different types of design of experiments. You would perform a full factorial when you wanted a foolproof method to test every possible combination of a set of factors. This would be generating all possible patterns. You will have to be willing to pay a price for performing all possible combinations, but the results will be less ambiguous. The number of runs to be performed is equal to the product of the number of levels in each factor. You would perform a screening DOE as a preliminary experiment to determine the most important factors in the design. It depends on the assumption of the Pareto principle that most of the variation in any system is generally due to a few driving factors. You would start with a relatively large pool of factors and narrow down the pool of factors to determine those that are most influential on the outcome. Typically, each factor would be tested at 2 levels, high or low. Typically, a screening design is a preliminary stage in a program of categorizing and improving a product or process. These can be more ambiguous as factors can be confounded with one another. You'd perform a response surface method DOE when you are trying to optimize and you have 3 or more factors to predict the response. We need 3 factors in order to create 3+ dimensional surface in our design. RSM would be a possible experiment performed after a screening design. There are 2 ways to do a response surface method DOE that the SAS-jump software discusses. There are a central composite design and a box-Benkin design. The central composite design is the most popular. It offers greater certainty of prediction near the vertices or extreme values of the factors than the box-Benkin design. There are uniform precision and orthogonal composite designs. These depend on the number of center points in the design and the axial values. The box-Benkin design only has 3 levels per factor and test points that are between the vertices, or extremes, of the cube presenting the ranges of each factor. We chose the bounce dataset. This dataset contains silica, sulfur, and silane as the variables for predicting bounce of the tennis balls. The bounce of the tennis balls is expressed in terms of a response variable called stretch. We chose to use this data set for the response surface method model we will demonstrate since RSM requires at least 3 predictor factors. We can use silica, sulfur, and silane to not only predict stretch, but optimize a 3-dimensional surface and find the optimal settings necessary for maximum stretch. Using the bounce data set, go to Analyze and Fit Model. For illustration, we will remove the factors that are in the Construct Model Effects section. Then select 3 predictor variables and click on the Action Arrow Macros button and select Response Surface. Then click Run to construct the model. To access the prediction profiler, you may have to click on the red action for Response Stretch, hover over Factor Profiling, and select Profiler to get a 2D view of the factors. As you can see in this example, it has already been selected. But we scroll down and the prediction profiler is shown. We can figure out the optimal settings of each factor to maximize stretch. We can click on the action button arrow for prediction profiler and select maximize desirability. As you can see, the optimal settings are 1.01 silica, 2.063 sulfur, 41.21 silane, giving a maximum stretch of 450. Now we will demonstrate how to profile and optimize using the RSM. To get a 3D view of the surface created, click on the Response Stretch action arrow, hover over Factor Profiling, and select Surface Profiler to get a 3D view of the response subject of the 3 factors. This just allows for a different view of the results in a 3D manner. This demonstration concludes our presentation. Thank you for watching.